Yeah.
Thank you. Okay, so we're at the start of the line because I've already started, and maybe I'll go through the overview of what we'll do next. But let me just continue to read. I'll give some big picture later on. All right, but one more point about this deformation. So I told you, okay, these are the topological lines. I can deform them, but there's a small caveat. Imagine that your equation of this bigger J might not be zero, but there could be sources here. Like there could be delta functions on the right hand side of suitable dimension, so here and two. I mean, that would not be that surprising here, right? Because I can have box 5, but I can have some sources on the right hand side. So every time I have that, those could be some localized points, and clearly, as long as I'm away from those points, I can deform my gamma as I want, but I cannot cross those points, right? Because then I need to use my Stokes theorem, and I will plug in this D star J1, but then I need to feed in the right hand side, not that it's zero, and I will get some contribution. So the rule of the game is now that they are topological out away from the insertions, but I can deal with those insertions. I can deal with the insertions such that I deform. So the insertion is here, and I jump over it, and then I use my Stokes theorem, integrate over this small area, use the right hand side that there's a source. There will be maybe some charge here, Q. And the thing which, this thing will basically read off that charge, right? It will return e to the I, a Q. Right? That will be the contribution from jumping over the delta function, right? And I claim that this is a way to think about symmetries in a better way, which allows for many generalizations. Namely, the symmetries are always some, for now, line operators in 2D. I'll tell you what they are in general, which act on the local operators by encircling them, and they read off the charges of the insertions upon pulling it over the insertion. There's many caveats in that statement I made, so I will rectify this now. So one caveat is that I didn't tell you what happens in higher dimensions. And also okay, so let's rectify these. Do I have it too long? Is it okay? It's fine. It's fine. So in higher, so I was just talking about 2D here, just to set up a scene. But if I were in I don't know, 5 dimensions, the suitable object I will be integrating is still a star of one form, and that's always a penultimate form, right? So I can only integrate it over surface of codimension 1, meaning in 5D it will be 4-dimensional hypersurface, right? In 3D it will be 2-dimensional. Usually I'll be drawing 3-dimensional and 2-dimensional pictures. So in 3D it would be some genuine surface. In 1D it's really one line, right? And so on. So that's one thing. However, the objects it reads the charge of are still local operators, right? That's like the genuine symmetry. Codimension 1 hypersurfaces and local operators. So that rectifies the first weak statement I made. The second thing is what kind of symmetries. So for now, it will be abelian symmetries. There's a whole endeavor to make this work for non-abelian symmetry. So I'll be only talking about abelian symmetries. U1s, it actually works nicely for discrete symmetries also. So not U1, but say Z3, Z5, something like that, which are also present in theories. And I'll show you an example of that.
And are they discrete? You mentioned Z3, that's abelian, but you said you will not talk about non-abelian.
Just
so what about non-abelian discrete? You will not talk about that.
Yeah. I know a bit about non-abelian symmetries, but yeah, maybe I'll tell you a bit in the end. So, but everything will need to be abelian and continuous or discrete. So continuous, you should think of a bunch of U1s maybe, or in discrete, some bunch of ZNs. Usually that's the case. And okay, so and now to the third point, that's the generalization. So now if you forget about the fact that you're correct, you were integrating over some surface originated from Nether theorem, but it would just be any form, right? I can have some form. Okay, so now I can go to something. Now I can have some form D, which satisfies the same kind of equation. D dagger is 0, okay? Or D star on chain 0. Sans the maybe some insertions, which we'll clarify. I can integrate. What can I integrate this over? This thing in the similar sense. So I have some JP. Now star of it will be n minus p, right? That's what happens with the forms. So I'm in n dimensional space now. Which satisfies this. I can construct this operator. And again, integrate it over some surface here. So what should be the dimension of this surface here? Not real surface, right? That surface is 2D strictly. Should be d minus f or n minus p, right? N minus p. Right, that would be the thing. I mean, maybe it's confusing. So let's say if I'm in 3D, having 3D, maybe I can have a two form, which will be something like this. In, now star will make it into what in 3D? One form, right? One form, and then I can integrate overall, right? Okay. If I had a regular one form, it would become this two form. So as you see, the previous that would be the previous example, just regular one form, right? And that would create two form out of it. Integrate over surface in 2D, and surfaces indeed link local operators in 3D, right? And then I can still roll. Right? If I have a point, right, you can pose it in a sphere such that it doesn't escape. If I just encircle it with the line, I can remove the point, right? Or I can just deform my line around it. So there's no sensible notion of a point sitting inside the line in 3D, right? Whereas in 2D it was clear, it was either inside the path or outside the path. Okay? Cool. Right. And so, but that's the thing. So now, are these useful things or not in 3D? Maybe they're not, right? Maybe they're not telling us anything about the point operators, but those are not the only operators we might have in our theories. There could be extended operators in the field theory. If people know any extended operators in in some theories. Maybe, well, in Maxwell theory, we have some. Yeah, so in Maxwell theory, you have your elementary field is gauge field, right? Maybe, but that's not really a good observable. It depends on the on what gauge you're in. Right? So it's not gauge invariant observable. You can maybe make out of it F mu, but you can also take a mu and integrate it all line, right? And that would be a Wilton line, right? So Wilton line is typical extended operator in some theory with something like Maxwell term in it. So those are so I guess that should give you a feeling that they are only present in every theory. You have gauge fields, you will have these line operators, maybe higher operators. But okay, the thing is that then there will be I claim that there's operators which read off something like a charge for these lines. Just like my codimension one surfaces have some charge of the local operators. Now there are some higher operators or higher symmetries which will link with these extended operators and read off their charge. Okay. So say I have a Wilson line. I'll tell you exactly what this is for the Wilson line in 3D, but just first let's do some pictorial explanation. So I have some line operator. Now that's the analog of this process. And clearly I cannot close it in a sphere that would be punctured by it, but I can encircle it by a line. Okay. And now there's a clear topological meaning to that line, this one, either passing through the circle or being outside, right? And again, like this circle, you should think of it as exponential of this star of the two-form. And as I told you, if you recall the Stokes theorem, you can deform this operator as long as you're sitting away from the insertion. Now the insertion is what will be a two-dimensional delta function. And then once I pull this away from the from my line, I will read off the charge of this line operator. Okay. Right. So these symmetries, ones which are reading of the charges of one-dimensional operators, we call them one-form symmetries. Okay. Whereas the ones reading of the charges of local operators, they were zero-form symmetries. And you can imagine that you can play the same game for k-form symmetries in dimensions. And I'll give you some example later on. But maybe to finalize this discussion in 3D, I'll show you how it works in Yang-Mills in 3D, or sorry, in Maxwell. Oh yeah, one more point, sorry, before I jump to it. There's an interesting thing for these higher form symmetries, where I don't have to talk about the point number 2. And that is that all these higher form symmetries, they can only be Abelian. There's no meaning of non-Abelian higher form symmetry. Why? Because there's no ordering on these lines. Okay. So if I were in the usual previous case, say I have my local insertion and I want to apply on it action of a codimension 1 topological operator, i.e. the normal symmetry. If I want to act on it with another generator, I would just encode it into another sphere and fuse those two on top, okay, or pull these two away from the point. But there's a clear meaning which one acts first and which one acts the second, right? So there's ordering, in how these surface operators are applied. But what about with the lines? I can apply one line and then the second line. But there's enough space for me to take this guy, pull it above, shrink it a little, and then kind of hide it in the, inside the other one. So I pull this one up, right? I make it smaller and pull it down again. So there's no meaning of ordering, and therefore you cannot really have non-abelian higher symmetries, right? Because on one hand, that would mean that ordering of the application of those generators matter, but here you see it doesn't matter. It should be the same calculation, right? Either one of them is I think first, or the other one is I think first. So that's something which should be noted.
So do you mean that like if you do this symmetries and calculate like the commutator, it will always be zero, or you cannot even define what it means?
Yeah, it will always be zero.
Okay.
On one hand, it's zero. On the other hand, it should represent some symmetry action, right? And then non-abelian symmetries, that commutator should not be zero. So it's inconsistent to define something like that. In zero for symmetries, it's okay. You can do this for symmetries which are non-abelian. It's just I will not discuss it because I will move to some extra stuff where it's not clear.
One question. In point operators, we have this notion of locality, right? Operator being local. Do we have something like that in extended object and in these extended operators, or is it the same definition?
I mean, they're not local operators. Right?
They're not local, right?
Yeah, but that's okay. I mean, there are such operators in theory. That we usually don't work with them because they're complicated to put in our correlation functions. But they might exist. I mean, they do exist, and they're significant.
Or maybe they're partially local.
Sorry.
I mean, they're local in some sense.
Sure, yeah, I mean, true. Okay, so maybe I'll just give you this example of what is this object in 3D maximum. And so as we said, there's this object we can make, which is the Wilson line. And I claim that the surface operator, this mu, is the right. So it's a do form, good, that works. Does it satisfy this or not? It does, right? Upon using the equations of motion, right? That is literally the equation of motion of Maxwell, right? So it does satisfy this divergent less condition. And
Would you call it J1?
Yeah, it seems to.
yeah, I mean, because it's one from symmetry current.
Okay, so that one is different from the P you wrote over there?
Yeah, sorry, let's see. Okay. Let's not call it anything then. Yes. Right. So, but it's divergent free, right? Except for possible insertions, and these possible insertions are in Rosen lines. So every time I can construct this operator. It's a surface operator. And B. And if I link my Wilson line through it, I will read of this vector. So maybe I'll call this U B sigma. And this one will call the gamma A. And the claim is So this is equal to this. But with an extra factor, which is the linking. So, I. And you should think of the A as a charge of this particular symmetry. Of the charge of the operator under this symmetry generated by the surface operator or line operator. I'm sorry, wait, did I scrub? I did scrub. I didn't do the star here, so it should be line, right? Sorry. Should be some other command. Prime. So this is still in prime. Okay, so I unlimit and I read up this phase vector, right? Yes.
So if you're using this Maxwell theory, then I can imagine some interpretation for like the point and insertions. So it's just some particle of the charge with some charge sitting in space. But what can I imagine for this part, for these extended objects? Is it like some wire which is charged, or is it more like a topological thing that like you cannot, like the charge cannot go there or something like that?
It's not electromagnetic charge, it's just the charge of this higher.
Yeah, but I meant thinking like an example that we're thinking about field.
So you should not think about it as a charge of other fields. There's no, so this is pure gauge theory, right? There's no extra matter. And there could be extra matter and those fields could be charged under variable. This is yet another symmetry which has nothing to do with the charge of the extra matter fields.
Yeah, all the higher
Yeah.
Are we in 3 dimension now?
Sorry?
Are we in 3
Yes,
dimension?
because I can draw for you.
Okay, but yeah, okay, that didn't really answer my question. Are we in 3 or in 4 dimensions?
2+1.
We're in 2+1.
Because one.
Okay, good.
Yeah. Of course, this will work in hierarchy. It's just that I
Sure.
can't draw it
Yeah.
nicely. Yeah, there will be special things happening in and I might get to it later. That has to do with this duality. Right. Is this clear or did I lose people? No. Okay. So, okay, should I do more examples of this? I'll give you a very nice example.
So what was, so you say U of B and then you got an A in, so where does the, see the A from the V? So how does the A come from? Is there something in that I should think of as picture as an operator in this here? Because I see you get an A. So you start, you have a UB, which have a B in it, and then you have suddenly get an A.
So you should really think about.
So are you saying that you are acting with a Wilson line on that, or is there something implicit understood here in the picture, which is not written in formula?
So Wilson lines, they are not only numbered by. So I mean, there's several moduli to them, right? There's a path on which I'm integrating. And then there's a trace or representation I choose them to be in.
Does this A has anything to do with the V operator you wrote here?
I don't understand. I just call it V.
You call it VA?
Yeah, it's the same A as in the exponential, right?
Okay, so where's the VA in that formula then?
There, it's the line.
Oh, that's the line.
Yeah,
Okay,
yeah.
good.
And I just called it that because I wanted to make clear what.
Okay, so in terms of formulas, I should think of U acting on V.
Yes. So these are new symmetries, and they might be useful. Here I'll just comment on why quite useful, not give you details. If I want to get to something else. There is, for instance, in the following fact, like, think of not Maxwell, but Young's now, and if you have Young's theory, if you just write down the Lagrangian, right? There's a trace. Those AMU fields, they are expanded in Lie algebra generators, and in principle you don't see a global structure of your structure group, right? What I'm trying to say is that you could write down Lagrangian for SU2 or SU3 and it will not really differ, right? So you would be like, okay, so it doesn't matter whether I have a theory defined for SU3 or SU2. But the statement is that they do differ. They don't differ at the level of local operators. Local operators are all the same. And the only difference is in the structure of the extended operators. And this information can be captured by these global symmetries. Okay. So they might be useful because this global structure of difference between a C2 and a C3, you would not be able to distinguish otherwise, except for the structure of these hierarchy symmetries.
So, if I can I ask one more question about this, this picture? So should I think of, so this cartoon, are you saying that, that when you move the circle outside of then it gets, the eigenvalue gets moved, get this e to the I, AB, is that what you think?
Yeah.
But does that make sense as it's it's acting on different objects?
What do you mean exactly on different objects?
I mean, it's different.
What is different from what?
It's not the same situation
As well.
as in circle. I mean, so we have done something to the operators.
No, I'm saying, okay, maybe it's I was a little sloppy. What I mean is that if I will have a correlator where I can have some insertions, but among which there's this line in the correlator, and this line encircling this this line. If I evaluate that correlator, I will get the same answer as if I evaluated a correlator where this line was unlinked. But the difference between them will be this extra factor, which will be pulled out of the correlator, which is just a numerical phase.
Right. Okay, but I get that this exponential has something to do with how we are linking groups and algebras, right? But you're not really using it. It seems not. I mean, you're not really explaining why you put the exponential in the first place.
It's exponential because of this, right? Because it's already in the exponential.
Sure, yeah, but it seems like it's on both sides. I mean, it seems like the exponential is just is almost like a what's it called? Something that's there. I mean, placeholder or something like that. It seems like the exponential is inert or spectator here. So you have exponential on one side, you have exponential on the other side.
I mean, this is usually how you think of boson lines, no? They are in the exponent.
And you haven't explained why.
Because I want the, maybe it's easier to explain in 2D, analog, okay? So in 2D, if I have compact boson.
Right, I guess first of all, the exponential, I mean, so you call it an operator. So what exactly is an operator here? What is it acting?
Just an operator.
So yes, an operator, and the exponential of operator is again, I mean, you can think of that as I mean, you can think of that as a Taylor extension or something.
Yeah,
like that.
sure.
Right.
But I mean,
Right.
like every time I'm doing a Wilson lines, it's always the path order exponential.
Right.
So
Okay,
it's-
yeah, so maybe another question. If I replace this exponential with some function, if would everything that you said still work?
Path of the exponential or?
Yeah, so instead of e, you got some function there.
Instead of I don't know, I mean. I don't think,
I think as long as the Taylor expansion has one like large entity, because we're talking about symmetries here, they have to be generated from identity. So
Yeah,
one that big though.
right. So, but he never explained that part, right? I mean, that's how groups and benchmarks are connected. And that's by an exponential map.
Mhm.
I mean, would it transform correctly if it's not?
Probably not, but it seems that much of what he's saying, what Ondra is saying, it would still work. I mean, naively.
maybe, yeah.
Anyway, go on.
All right,
The agent. That's important.
okay, so, yeah, so just keep getting more, so I'll talk about a very special class of simple theories where interesting things happen. Which hopefully elucidate some of these facts in concrete terms. So the theories I want to talk about are called the theories. So I'll show you how they are good playground for these generalized symmetries and what kind of generalized symmetries they yield and yeah. So what are these theories? They're sort of non-chiral version of transitions. They are free. There are three theories, first order free theories of this kind. And here I need to tell you what dimensions I'm in and what are these P's and A's, right? So in general, in dimension n, these two need to add up +1 to dimension of the space, right? Otherwise they can't integrate. So it could be a K form and n minus k minus 1 form, right? And so there's always several DF theories in any dimension. So in particular, say in 3D, I can either have some 3D, we can have a theory with a scalar 3D and 2 form, or 1 form and 1 form, right? Those are the only two options in 3D. Okay, so let's look at these two types of theories. Because they are interesting. So every time, what will be crucial is that these B's and A's, and here 2 form and 1 form, they will be something like connections. Technically, 2 form will be a bit jerk, a Gaussian jerk connection, yeah.
So in your case is B is into form.
Sorry. So here, this is 0 form and 2 form, and here it's 1 form. And
So maybe you should call it something else than B.
maybe, true.
Or just label it the form,
Sorry.
or just label the form.
Yeah, but all right, C, maybe C. C is good. Or I mean,
Better not before.
okay.
So maybe the white.
Right.
Yeah, I'm suppressing, but yeah. And here. So these are the only two types of gift theories on 3D, and let's look at how There are three theories, so in principle, I should be able to calculate all the correlators there are in that theory. Let's look at what are delegation variance operators and what are those linkings I was talking about. Okay. So let's take the case one first. Case one. There's two important distinctions which will be crucial for later, and that is as to whether there's issue three, but I will only discuss two, and I can refer you to literature for the middle case. So it's either that phi is compact, and C is Q-form in space with even values.
Bias compact means just like show zeros on.
No, I mean it's a compact boson. It's
Oh.
it has values in U1. Okay, and these are two forms with values in U1. Right, they're not really two forms. They're like gauge fields. They're observed connections, but let's think of them as two forms for the moment.
So yeah, the target space is compact.
What?
Target space is compact.
Yes. I'm saying connect. Oh, and this one. Alright. They're not really connections, right? They're two forms, but they have one form gauge symmetry, so they're Chern connections. Or they can be both valued in rings. Okay. So this is one A and one B. Can be compact or real. And again, connection, right? Right, so what are the operators I can construct here? Same for this one. There will be just both two forms valued in one or R. Okay. And there will be similarities. So what kind of operators can I construct? So first phi, maybe I'll do compact and real. Now real type 1 and type 2.
And
Yeah.
the other one where you have CP5, you're saying that that's a total derivative of away from your phi DC.
So sorry, phi.
The last option in 3D would be two form D zero form.
Two form, zero form, and this is one from one form. Right?
This is
Yeah. But you could also have two form D zero form, which
That's
would be
this.
no, that's a zero form D two form.
Yeah, but that's I can.
Exactly, that's up to a total derivative.
Yes, that's why I didn't include it. Yeah.
Yeah.
Okay. Yeah. Yeah, I mean, let's see. Right. So if phi is compact, that means that it's defined up to 2 pi thing shift, right? And that means that phi in and of itself is not a good operator. But if I put it in the exponential like that, it becomes good if I tell you if I specialize A, right? And I need to specialize it to what? What does it do? Integer, right? Yeah, it needs to be an integer. If A is integer, right? Same holds for C2. So C2, the thing is now that C2, thanks to it being Jerv connection, there could be large gauge transformations, and in principle, this integral, dC2 over bulk of some three-dimensional space might not be zero, right? That's for any form, but it needs to be in 1 or 2 time set. And that tells me that I can again make just these kind of things, but only for B being in Z. Right. Right. For real though, doesn't matter. Here I can construct anything, any five, any CQ. No restrictions on A and B here. Whereas here they're restricted to be in integers. Those A's and B's. But in here it's the same. It's just two types of lines. Several lines made out of A's and B. If they are U1 valued connections, there will be quantization condition just like this one on the surface, and that will restrict A and B to be in Z. Whereas here, they're just whatever you want them to be.
Now you're not putting stars in the operators. Last time you put stars on.
Star. What star? Oh no, no, just yeah. Yeah. So I claim that these are topological operators because why are they topological, all of them? Because you see that whenever I vary this action with respect to well, this one yields these two equations of motion, E5, E2. And I think that's why I didn't do the star. And this one is an EA and an EP. So for each of them, I can do my Stokes theorem trick, right? Every time I take either these surfaces, or I'm moving these points, or I'm moving these lines, they always, I can wiggle them as long as I don't cross any other insertion, right? They're all topological operators. So these theories are very, very simple, right? They have just a bunch of topological operators, but they're not fully trivial. They're almost trivial. We'll look at how non-trivial or trivial they are. So what decides about as to whether they are trivial or not is the three-factor n. That n there is total level. So this is all what makes them trivial or non-trivial. This one. Okay. And why is that so? I will give you
Again, ask about the C2 case again, so now maybe you could sort of define it a little bit more, like when you say C2 is a two-form on sigma with values in U1. What does that mean? What is sigma? And what does values in U1?
I'm sorry, sigma. I meant just to form in full space.
It's a full space.
Full space, right? It's just this is defined on some m, and this is m. Correct.
Okay.
Just
So then that integral is an integral using Stokes theorem. The integral over the boundary of sigma 3.
yeah, I mean, maybe it's easier here, right? Because in for connections, I know yeah.
Okay, maybe so tell me the second. What do you say? So for
So here, what I wanted to say is that if you have a one form, right, in 3D, which so if I have just one form, right, create two form like that, over a closed surface, it's zero, right, it's zero. But that's not true for connections, right?
Okay,
Because of the large gauge transformations.
yeah.
But if they, right, because I need to, like, we usually, like, I don't know, I take a sphere in 3D, I cut it along the equator. I know that a plus and a minus can differ by d5.
So
And
sigma 3 has, there's no boundary.
no,
There's no boundary.
yeah,
Oh, that's what you, yeah, because you said it's compact,
yes,
there is no boundary, and then you get this topological condition.
yes, yes, yes.
Yeah.
So yeah, it should be an analog of this quantization condition. Like I cut it along the patch overlap. I use the fact that there are large gauge transformations, but they are U1 valued. So at least I know that it's valued in Z, right, or multiples of Z, or multiply. And that's always
So are you saying that the B and the A and the C and the phi are not globally defined?
no, they're connected. They're functions.
So they're not globally defined?
No, just like, I mean, here it's not surprising, right? Those are just gauge connections. For C, it's a little weirder. I'm not getting into what it means because it's weird, right? You need these triple intersections and it gets a little messy, but if you forget about it and kind of pretend that it's just one form case, it kind of makes sense.
So, so how would you write that properly? So when you say that C belongs to omega M, and
I don't know.
so this is
There's
simplification.
probably
It seems like it's globally defined there.
Yeah, that should be this good pretty much. I don't know what's the right sense for chairs. Maybe let's call it G. Or I don't know. But yeah, sorry. Yeah, but we know what. Yeah, they're just like H fields, just higher dimensional H fields. Okay, so let's now look at what. So this prefactor is all what matters in these theories. That will make them into whether they're interesting or not, at least in the compact case. In the real case, so yeah, the real case, the quantization condition is not there because there's no large base transformation, right? They're just valued in R and that will impose any condition like that. Okay, right. So, so the compact case now. In compact case, let's take this two form, zero form case. And look at what happens if I have e to the q5 and e to the or purpose. Right? So I can calculate. So if I were if I had time, which I don't, I would really have to find the propagator. That's easy, right? It's a free theory. I would actually calculate this two-point function by evaluating. So by finding a propagator between this guy and this guy at a certain point, and then I will calculate the surface interval of the propagator, and I will get some linking number. That can be all done. You can do it as an exercise. It's fun. It's and it's not that hard. But again, like I can use this abstract logic of moving this one because it's topological, and I'll move it, then I pull it through. That will result in some delta function insertion, and I claim that now the phase which makes it different from unlinked operators is the following, and that's crucial factors entering here. Q and V. Okay, so the N enters here. Okay, and now you see that Q and P, they are a priori in Z. But what if P or Q is a multiple of M? It's like this will be 0, right? Or sorry, this will be 1, right? The exponent will be proportional to 2 pi or something. So if any P, Q is a multiple. Okay. Then I see that this is 1, right? And this,
I think you should take away the comma in PQ. I think it should be a product.
no, I'm saying one of them is, I want one of them to be n times Z.
Well,
Are they prime?
you could fulfill it more easily.
A priori, they are, so Q and P, they are both in Z.
Are they co-prime or something?
No, they're any Z.
Any,
Right, any Z squared, right? Could be
Right.
1 and 3 or whatever, 2 and 2.
but it seems like you only need that the product of them is a multiple.
Sure, but yes, but I want to make a point that anytime I have one of them in n times Z,
That's a special case.
regardless of what is the other one, this correlator will not affect my entire correlation function, right? And we call such operators transparent, right, for obvious reasons. So if P is a priori in this lattice of Z, if it's in Z, any Q is transparent, any Q doesn't feel this one, right? I don't want to see. So P is in NZ, Q doesn't feel it, and vice versa, right? Right. So it seems like an ambiguous description of a theory, and what you should learn from that is that instead of having these two types of operators, P and B Q. Okay, so this is for C, so this is fine. With these P and Q should really be ZN. Right? So you see that there's some effective description of just as discrete form symmetry. And same will be true for one form, so it's the same logic. Okay. Right, so that's the compact case. Compact case.
So M is equal to 1 and everything is just.
Yes, exactly. And that has been known for the longest time. It's in some involved Witten's papers that the theory of Witten is trivial. Kaputkin papers on that a long time ago. So yeah, so specifically for an equal one, it's trivial. Yeah.
If I do this, if I'm pulling out this two form or operator out of this form, we're getting this factor. If I do this step multiple times, say n times, capital N times, it will automatically give me 1 without any conditions on Q and P.
You mean like the sphere would be linking the?
Yeah, I mean do the same operation n times. Like put the operator back in, then out, in, out.
You also wanted to put that in.
I mean, you could also, you can apply several of these spheres. Clearly, you could also, well, I don't know if clearly that's, you can fuse them first, and the fusion of these surface operators just means that you're adding these charges, right? So if you take that simple one with equal 1 and apply n times, you'll make this composite sphere which has charge n, and then that will become transparent operator. So it will read nothing, right? So that's also consistent with this flow. Right. Is that clear?
Yeah.
For the real case, I said that I missed out one case, which is when one of them is compact and the other is not compact. it's just sort of, you can basically do that as an exercise after you understand these 2 points. It's just combination. For the real case, it's simpler because you see
What?
that, yeah.
Was that, by the way, why you say you want to include in discrete solutions?
Yeah, I mean.
Basically.
Yeah, and you'll see that this one, here we won't have discrete. It will be something else. Right. So here, the factor is the same. But the fact that both of the Q and P are in R, I can just hide this into rescaling one of them, right? And it doesn't stretch or shrinks anything. It's just the same continuum. So N doesn't matter. Some people say that, okay, I can just subsume it in the field, but it's kind of interesting to do there because you cannot do it at the level of the compact ones because, yeah, I don't know, it's better to say here. Like the N doesn't matter because you can rescale one of the 2 continuous sets of charges. So here the level doesn't matter and you just have this. And some of them link, some of them don't link. Okay. So there's nothing to be said here. And yeah, there's just R times number. The 9th one we've started with just survives. I mean, of course, there's always some. There could be. What if Q is 1/3 and this is 3? It will be mutually transparent. What I had in mind here that there is a subset of lines which are transparent with respect to everything else, right? That's why I mod it out. That's why I end up with ZM. Whereas here, there's always, if I fix one here, I will always find at least one guy here which feels it, right? I cannot drop out some subset of operators. Right, okay. Okay, so now I will, go next. I already spent 1 hour, but I want to show you something when you start adding boundary to these PF theories. So can I speak for like one more, I don't know, 20 minutes, 30 minutes?
Yeah, you should just be done by 3.
By 3? Okay, I'll be done earlier than that. Okay, right, so what can I do? Right, so it's now suppose that I have I don't have the 3-dimensional closed manifold, but I will have a boundary here. And I will have one of these theories and I'll tell you what happens in each case. So now my 3 manifold has a boundary, 2, 3, and I have one of the theories in bulk. Okay. So in order to study that, I need to specialize boundary conditions. And I'll tell you how those boundary conditions differ based on which group selection I have. So let's first do compact case. So you see that I have these U and V lines. They have charges P's and Q's, and they are both in Zm, right? Zm squared. Right? So there's 2 simple types of boundary conditions which I can implement. Let's do the one form case now. Okay, so one setup where I get one form so the DNA. So I have 2 types of lines. Those lines need to be closed in the bulk, otherwise they would not be Gaussian variant. But I can can enforce some type of boundary conditions which will allow for some of the lines to enter the boundary. What I mean by that is that if, for instance, I require that A is 0 at the boundary, and B is whatever, 3. So this should all be required normal. Then these are the A lines and B lines.
So I think that's not called Neumann.
So which B are we talking about? There's so many B's here.
I don't know.
A at B, what does that mean?
I should, this, no. Curly B, that's a curly B.
Okay.
And these are the one form case fields.
But is it free, then you don't have a condition.
Yeah.
So why do you call it Neumann?
Sorry,
Yeah, that's not nothing. It just
It's nothing, yeah.
it's okay.
So Neumann means the derivative is 0.
Okay, let's not call them. Let's
Thank you.
just call this one usual. Usually people call it like in the BF theories, but yeah, it's maybe a bit of a. I mean, it's all wrong here anyway because they're first order theories, so it's only in the second one.
Do you need A to be 0? If only DA exists in the.
If should what?
I mean, the DA you have action, no?
Yeah.
So isn't like A equal to constant sufficient to satisfy the boundary condition?
I want to boundary condition will be that is that the boundary should be 0, right?
From the Lagrange.
Yeah.
Yeah, because you want to take out the D from both. Okay.
Yeah.
And by the way, there it makes a bit of distinction whether you say BDA or ADB.
EDA. Very well. Yeah, sure. Yeah, now it matters because now I have a boundary condition. I cannot use the integration by parts. Yeah, that's true. So this is one of the possible boundary conditions. What happens there is that I can now have my B lines, which are just anywhere in the bulk, or maybe even sitting at the boundary, because I haven't specified, and they can certainly be placed in the boundary, right? But the A lines, they need to be, well, they either can be in the bulk, or they can be attached to the boundary. So these are A lines. Right? They are the A lines, and now interesting things that yeah, so A lines, B lines are just like that. Lines. And cool thing about this BF theory is that it kind of realizes in a quotation marks holographic sense these form symmetries at the boundaries. So you can now think of these insertions. If I forgot about the bulk theory, that there are some local insertions.
So this is the third version of A and B.
Why? Why, where? These
So-
are B lines because they are associated to the B.
Oh, so it is associated.
Yeah.
Okay.
And A lines, right, because they are 0, they can be attached to the boundary. So now I have some, I can think of this 2D system as something what has local operators. They are the ends of the A lines, and it has a Zn symmetry. Zn symmetry, and the Zn symmetry is generated by these B lines encircling the A lines. So I can first well, so if I can have just purely a 2D perspective, I can just encircle that insertion with the B line, but I know that I can deform it to the bulk. I can move it up, and I'll just have that factor e to the, yeah,
One question, like when you say you plug this, let's say B circle out of A line, you're crossing it, right?
yes.
Can I do like, for example, that's B, you go there and then.
I cannot
Assuming
say
A-
this goes in,
Okay.
this one, because if this stopped at some point, it will transform with the gauge, transformation and will not gauge there.
Let's end on the boundary again.
Sorry,
Let's end on the boundary.
it can end on the boundary again, or just go to infinity.
It's not-
If it's not, yes.
Yeah. But here I'm just thinking one boundary and, well, yeah, I mean, you're right, like it can come back here for sure, but it can also go to infinity. Yeah. There is also setups where there will be another boundary and, based on which boundary conditions I will choose on the other side, that will maybe put some extra conditions on the lines I have. Okay. There's a nice, here's a nice caveat to what boundary conditions I can have in the compact case. I'll tell you that shortly. So for now, so clearly I can also exchange this, right? B line, I mean, it's almost the same, right? B lines can end at the boundary and B lines can be free. It's pretty much interchangeable. But there's one more thing which is not so clear from this boundary term, and that's the following. For that I need n which is not a prime. Okay, so if n is prime, these are the only sensible boundary conditions. If n is not prime, if n is, I don't know, p times, well, not pq, we use pq. I don't know what are other letters.
I is,
What?
R is.
A and B is.
And that's not. And, well, yeah, S and P. If it's, well, just not prime, whatever, something. And let's maybe take it to be 2 times 3, right, just to be concrete. So maybe S is 3 and P is 3. So there's a product, I have Z6 times Z6. Okay. A lines and B lines are charged in this lattice. And these boundary conditions still hold, these are generic, right? But I can have something more interesting happening, where I let some A and B lines turn into boundary. So, right, so notice that here there are, rule of thumb for these boundary conditions is that the only lines which can end at the boundary at the same time are mutually transparent, right? So that was the case for A lines, right? All A lines did not feel any other A lines because they have trivial linking among themselves. Same for B lines. But here I can achieve that by some mixed, in some mixed sense, right? Why is that the case? Why can't I have,
Oh, I see, so you can have both A and B lines ending, but they have to be multiple from something.
Exactly.
So
Yeah,
from somewhere.
And why is that? Like, imagine that I had 2 lines which can end at the boundary, but they have linking, right? So if that was the case, I have this line which can end at the boundary. I have also another line which can end at the boundary, but I will make close thing out of it. If I pull it at the boundary, it will become trivial because my boundary condition tells me that it's 0 at the boundary. And now I can just open it and circle my insertion. Then I can pull it to the bulk, but there I can pull it away and create a face. So on one hand, if I do that calculation at the boundary, I get nothing. If I do it in the bulk, I get a face. So that's wrong, right? That's inconsistent. So that's why I cannot have mutually non-transparent lines to end the boundary in this one consistent boundary condition. But yeah, here what can happen is that I can choose some subset of Z6 and Z6 of A lines and B lines, which can end, right? Because I see that now six EQ. If, for instance, my A lines are in Z3 inside Z6. They will be mutually transparent, right? And they can both end at the boundary. That was not the case for prime n, right? Because I could not trivially factor just in and have one subset and the other subset end at the boundary. But here I can do it. And I can have any Z3 lines, so Z3 A lines, and Z2 B lines. Because they're all mutually transparent. And now, what are these symmetry operators we survive? They are exactly Z6 modded by Z3. So all the Z2 and all the Z3, the remaining guys of A and B lines are the symmetry lines here, because they do link non-trivial with this guy and that. So I can realize a theory which has a Z2 Z3 discrete symmetry. At the boundary. Difference is though that these product symmetric groups, they end up being mutual. They end up having close anomaly at the boundary. So this theory will have these two global symmetries, but they have close anomaly, meaning that if I gauge both of them, I'll lose the action won't be gauged current. That's always the case with these mixed boundary conditions.
So can I?
Yes.
So you're talking about link, so the two lines you wrote, you're talking about Lincoln and American, but they seem like they're not intersecting at all, right? So do you want one of them to be like a circle around the other that is the whole surface of the boundary? Or maybe I just don't understand the last part. So you have these two lines, and you're calculating the linking number between them.
Yes.
But they don't seem to, you know.
No. Here I was just saying that both A lines restricted to some sublattice and B lines can end at the boundary. Okay? And the complementary guys, sure, they would need to link them. Okay? That's the way we left the charge.
Oh.
Right. Yes. Yes.
Does it always become a direct product of these discrete subgroups, or could we have a semi-direct product or something more
Well,
complicated?
you could have that also, but it needs to be. It would be reflected in the Lagrangian, because this is not the only thing I can write down in BF theories. For instance, you can imagine I would have that case number 2 with one forms, and maybe I would add in one ADA. That's also something you can write down, right? And then there would be some non-trivial interplay between these vectors. So this is the simplest vectorized base. Of course, it's heavily form dimension and about dimension dependent, based on what terms I can write down. But yeah, you can do more crazy things. Sometimes you can have like lines ending on surfaces and all sorts of weird things. Okay, and now go to the real case and show you how one can talk about some duality in that two-dimensional theory, or something like duality. Okay, so let's analyze that one case in 3D again, but with the real group. So I have one form, or two gauge connections, A and B. They are both valued in R. And now what are the boundary conditions I can have? Right now, to recall from the table I just wiped down, I can have these operators. These operators, they have mutual linking. There's no restriction on A and B. And it's only this guy which links with that guy. These are mutually transparent and these are mutually transparent. So the most most natural thing I can do is that I will let these end at the boundary or these end at the boundary. And in that case, I'll have I will have theory with the spectrum of some local operators, which have charges R, right? So these will be the ones ending in the boundary. R will number all the possible local operators, and then there will be some R form, R symmetry. The boundary made out of the closed operators of this kind. It will infinity, right? I can do something more interesting, and that is that I do this mixed boundary condition, and that will be what will that be? If I look at this 2 pi I can I can allow for A to be in R times Z and B being one of them R times Z. So this R is a parameter for now. It will play a role of some radius of a compact boson, but it's just something what enters in these boundary conditions. Clearly, if I feed it in, these are integral valued. I get a trivial linking. So this subset of all the line operators in the bulk can end at the boundary at the same point. They are all mutually transparent. Okay? And as it happened there, the symmetry operators, which can act on these lines, are the original spectrum modded out by these subsets which can end, right? It's the complement. So here I take the first vector R and I mod out by this R Z. And here I take the second R, make it 1 and 2, and then mod out by 1 more R. Well, both of them are topologically ones, right? But I claim that they're somehow dual to each other. And so now I have a theory which has a Z2 topology, so these two are still set, right? It's just that one is more stretched and the other is less stretched based on what R is there. Spectrum of operators. Boundary and lines. And there's a U1 times U1 symmetry. Acting on these, one reading the first charge, the other is reading the second charge. I claim that this is, and again, that's something I cannot really show you now. These have mutual Hopf anomaly. So now I'll tell you which system realizes that in 2D, and then I'll maybe quickly comment on how this theory can be this bulk extension of the 2D model, which is discussed now. So that's that. So the model, which typically has this anomalous U1 times U1 symmetry, is a compact boson. So at the beginning I started with compact boson, but I didn't tell you about all the symmetries which are there in the compact boson. Have people heard about S-duality or electromagnetic symmetry in Maxwell?
I don't know what exactly you mean. Right.
I mean that there's sort of mirror or dual description of the usual Maxwell, and my basic degrees of freedom in Maxwell are mu, right? Each fields, but I can do this duality transformation where I construct a mu. I take the start of it, and I find the D dual of this, right? And that will be the dual description of Maxwell.
Is that the same on the A and B?
Yes.
Yes. Yes.
And now you're in 4D, right?
Unfortunately, yeah. I'm just trying to mention this because the model I'll describe is just a even simpler manifestation of this duality. And that is the 2D boson, so 2D compact boson. So 2D compact boson, it has the. I wrote my function at the beginning, and I told you that this is one of the currents. Right? It's one of the currents, which I'll call maybe UFD, electric. I'll call this electric current. The D dagger of J is 0 if the equations of moments are satisfied. But there's also another J, J magnetic.
What is the dagger?
D dagger is D dagger. That's the dual of the D.
It's star D star.
Oh, you defined it before.
Yes. Yes.
Star D star.
Yes. Yes. Sorry. I can also define this guy, which is sorry, you call it star.
Well, you can write it, you don't need to introduce this, you introduce the star, you have the D. So
Yeah.
you can write it in terms of Hodge.
Sure.
Indeed.
There's also this guy, and this is a star of the I. It's not proportional to this, right? It's a whole other current. One form D dagger of it is again 0. This time it's even better because I don't need the equations of motion to show it because it's literally just D dagger and J are different. And the star, the stars are defined. It's always 0, right? Because this is proportional to identity to these square root of 0, and I can make it equal to 0. So there's these two currents, and this one is a bit weird. They're both global currents, so I can make these two operators out of them. So you electric. Right, and Q magnetic. They're both topological, but what kind of symmetry they generate, that's tricky. So for this one, I discussed that at the very beginning, that it's something associated with a shift of my compact boson, right? So it should read, it basically reads off the charge of these vertex operators. It reads off this P. But this guy, it has no knowledge of reading of some charge of fundamental operators. It reads of the charge of vortex operators, or what is it called? What people call one of these operators. Disorder operators, thank you. Of disorder operators of this model. And they are basically something like this, but made out of dual phi. What I mean by dual phi is that I can define this d phi would be some f. And you see that I can solve this f to be d of f, d of phi, but I can also ask, is there another degree of freedom, phi tilde, which is a potential for the dual curvature in a way in 2D, just like in 4D and mills. And that would be my f tilde. And I can have operators like that. And these guys will read off the Q of that. So there's two types of operators. There's these ordered operators, normal vertex operators, and then there's these dual or disorder or magnetic operators. And this guy reads off the charge of that. And really the full spectrum of operators of this 2D boson is I P I plus Q phi tilde. Or if you're a string theorist, and you like P and this is really the winding of the string vertex operator. Maybe I should call it. Okay.
Is there any difference between F and J in your model?
No, I was just gonna, use F to make it clear that it's just like as well in 4D. But yeah, it's J, which is. And the claim is now that you could. So this is a model which, and now, okay, so what is the, if this phi is compact, it again is defined up to shift. So these P's are in some R times Z, sorry, one R times Z. And these guys, you need to trust me now, they are connected to winding, so they tell you how many times your zero mode of the thing points around this one. So it will be more R.
But now it's a bit confusing because you used exactly that notation, which was for the non-compact.
No, it was not in the group in the target, sorry, in the bulk, but the symmetry operators are the compact group because it's R mod these. So that's the weird thing in the bulk. everything sort of gets unified, right? You have
Yeah,
this-
but you know, when you talked about the compact motion before, the period was too high, no power there. And you just have an integer, the R was 1.
I mean, here, yeah, okay. Here pi, if it's defined up to 2 pi r.
But before there was just 2 pi.
Okay, yeah.
And now this, rather than connecting to the previous case with the compact motion, connects to that
Yeah,
case, which was really starting somewhere.
that's true. Yeah, so here I'm thinking it's also parameterized by this r. That's what makes this one r z, and that's what makes this r and z. Yeah, sorry.
Can I ask?
Yeah.
So this existence of this pi tilde, this dual pi, that does not depend on the tag space being compact. Now you can define it here for non-compact space by doing solving this merge of f equal to or something.
Yeah, true, but
And that's
it's a bit
the,
weird with the lattice, right? Because if you think of it as some.
yeah, I mean, it would just not have non-integer pi and omega, it just be real numbers.
I don't, yeah, but I don't know if you want to talk about disorder operators in the, I don't know, there are a lot, right? There are not a lot, because really, there's another way to think about these disorder operators is that it's purely in terms of phi, is that it just tells you that it's some insertion of whatever, some kink in your field, such that if you calculate the volume around it, it's 2 pi times some number.
Yeah.
But for the non-compact boson, that doesn't really make sense. There's no winding. You cannot really create any winding, like non-trivial logical winding. So I think we should really talk about this strictly in the.
But these two equations,
I mean, this makes sense in, but I don't think this chart computation will quite work out.
yeah, of course, it will not be content.
But yeah, I mean, this equation makes sense.
Yeah.
Sure, yeah. Yes. Yes.
Yeah, thanks.
Okay, just so just to wrap up, I'll tell you how this one can be now with this chart. But yeah, it's weird, right? Because here you see that everything comes out of the same thing, right? Like you have lines which are in the bulk, and some subset of them will give rise to physical operators, and the complement will be the symmetry generating operators. So that, and also, I mean, it's surprisingly new realization that this is how you do the compact boson, because you need this non-compact group in the bulk. And then modeling out gives you the compact group, because before people always just study the Chern values in compact groups, and they only got these discrete symmetries at the boundary. So you really need to go to these non-compact cases to realize some continuous symmetries at the boundary. Right. Yeah. So how do you how can you now construct this 2D boson as a boundary theory for some 3D space? If I now consider this slide. With boundary conditions to be so. Well, here again. Both values in R. Actually, I will now have boundary conditions on this side, so B1, which will be the following. A. 21. will be some delta. So what I mean by that, this was a one form in 3D. Now I can restrict the boundary. It's a one form in 2D. And if I provide you with an extra structure here, namely a complex structure, I can decompose it into dz and dz bar. So these boundary conditions tell me that dz bar part of A is 0, and dz part is some del phi. And this one will be that dz bar is del phi, and the other one is 0.
So you need to, right, point out that this is not just a partial derivative. Right, it's like the
Yeah.
complex version.
Yes. So what I mean by this is that dz. Sorry. Yes.
Operators.
Oh, sorry.
Yeah, the Dolbeau operators.
Right. Yeah.
You probably want to do it in the opposite order.
What I want to do was probably. What do you mean?
Anyway,
And it looks like you're differentiating the DZ. That's,
I see. Okay. Yeah. And on the other side, I'll use that familiar boundary condition. So this one in and of itself would not be not using good. This would still not specialize the spectrum, but on this side, I will decide which of all the lines can end, and I will do it in the same fashion as we did here. I will put the boundary condition which will tell me that out of these lines, I only take the A in one or line. Sorry. So and B one.
if you have this action, how come the boundary conditions are so symmetric? Like if you're, calculating, varying to get the equations of motion, when you're varying with respect to A, that piece will have to be partially integrated to get the equations of motion. That means that your boundary term will be B variation of A. And then it seems like, you would put naturally different conditions on B and A. So how come here it looks like very symmetric on one boundary, you put conditions on A, and one conditions on B? Does it make sense?
Sorry, wait, this was one, so, sorry.
Was there one?
This was.
Yeah, so okay, then it's even more symmetric. So how come it's so symmetric when isn't the action supposed to be like written in terms of Delbo operators where one is on A and the other one is on B or something?
I'm kind of find it in terms of. Just
Yeah, it's in three dimensions.
Yeah.
But how do you get it so symmetric?
I guess what Richard is pointing to is if you try to now look at the boundary term, I guess you have to do an analysis of the boundary term, which is 2D, and then see that there's no contribution when with this is consistent.
Right.
Right, so I guess you get delta B A plus, I guess, B delta A.
Why would you get both? I would
So
say just
because you're varying both, right? I mean, you're
right, but you only partially get.
yeah, but the delta is not a part of it's a indivisible variation.
Yeah.
So if
But you
you,
don't need to partially integrate the boundary in V. It's only.
oh, sorry, you're right, you're right. So you only one of them, yes,
So on the boundary have B delta A. So what is that?
yes. B did, right, B did, right. But I guess it has to do with. So it's,
So the boundary, yeah, the boundary of the thing which survives is in.
So
Probably
the other way.
B delta A.
I mean. These are not really, so for these, I really need to support some extra boundary terms to cancel that out.
So this is not the full action.
No, no,
Okay.
yeah, there's extra stuff I need to add to this. Which is localized at boundary so that it cancels out, which is exactly those size within boundary.
I see. I see. So there are 5 terms.
Yeah.
Okay.
Sorry. But now I see that I'll have these A and B lines ending at the, so now A can end at the boundary here and there. If the chart is restricted to be momentum like, and B lines if the chart is finding well. And the remaining guys, the ones which are in the lattice modulo, the things which can end, they will exactly be these kind of symmetry generators.
So when you say one thing like is one of the 5 to 5 tilde there in the boundary?
Well, it's more, yeah, I mean, five, yeah. Be really, yeah. Well, the thing is that it's more like, sorry, it doesn't matter. Phi is really like a big phi, which is phi of this phi level r plus phi right and phi go back. Minus phi right. And then this one must do only half of it, right?
Okay.
And then the thing which I will probably not get into because it's been way too long, is that you could also now, so I claim that this realizes the so-called symmetry TFT of the 2D compact boson with all its symmetries, topological and normal ones. And there's another operators which can be realized in the bulk, which is the T-duality operator. But this T-duality operator, it would not be just a regular line operator, but it will be some surface, which is so-called condensation defect, like operator. And it will act on these lines, and it will flip the A lines to B lines. And it will, as such, it will be a T-duality operator. But it's kind of fun because you see, T-duality is really, it's not a symmetry of your compact boson, right? It's more of a symmetry on the full modular space of your bosons, right? It sends momentum to YDs, but it also changes R to one or R, right? Or some factors. But this bulk theory doesn't really know about which radius I chose. That is captured by this boundary condition, namely by how sparse is this lattice and how snug is the other dual lattice. And however, I can construct these operators, and they act on the generic spectrum. But they are such that they are trivial in the generic radius point, so there's no action basically. They are zero, so they're kind of trivial. They're duality in the self-dual radius, where you expect it to work nicely, because there is really self-dual symmetry, right, on the self-dual radius. And they are also non-trivial at the rational multiple of the integers of the radius, because the thing is that there. It will not be just T-duality symmetry, but it will be T-duality symmetry composed with so-called discrete gauging. Discrete gauging is something what blows up the radius. So what happens is that you have a self-dual radius. You will be in this R1 and you'll be sent to one over another. But then there is another symmetry which stretch out the radius back again. And these condensation defects, they are a composition of T-duality and the discrete gauging. So they do this weird loop. And the discrete gauging, it sounds weird, maybe. It's really just that I take my vertex operators. I send these, I act on them by shift symmetry, which is valued in k times 10. Where and discrete gauging means that I just keep the ones which are trivial, which are trivially charged, and this is that k symmetry, which means the ones which are kth charged guys in the original lattice, which is as if I was effectively on a different radius, right? But that's a weird symmetry. It's so-called non-invertible. It takes some guys, it throws them away, and it just keeps the others. So this condensation defect, it will have various phases. It will be zero on generic radius. In rational radius points, it will be non-invertible. It will throw away some lines and keep the other, and on them it will do something like T-duality. And only in the very, very special self-dual point, it will act as a bona fide invertible defect on your spectrum. So that's a fun thing to.
So if it's a surface, can you draw the surface in your picture?
Yes. Well, yeah, it will be something like this. It will stretch from one boundary to the other, and it will act on the lines which are stretching from one boundary to the other via linking them. So.
Yeah, but this is now space-time diagram. So where it's 3 dimensions, boundaries are 2 dimensional.
Mm-hmm. So
how does it act?
It will be 2-dimensional in the bulk. It will have 1-dimensional imprint at the boundary. So it will be line operator at the boundary, which facilitates duality. And
yeah, but somehow it's not like it changes the whole theory. I just have some other diagram where is the T-dual theory? I have to move the stuff around to get the T-dual stuff, or
so yeah, it will be weird because what it does is
everything I have inside works like
So the interpretation then at the boundary is that whatever is inside this disk will have to have different lattice choice for the boundary ending lines, and whatever is outside will be in the T-dual theory. So it's really like a boundary condition changing operator at the topological side.
Wouldn't it be better to make it like this, and then you sort of have one half of your space is T-dual, and then you move everything up, and you get T-dual.
You could also do that. You could also.
It doesn't have to be a silly.
No need for that. You can also do it in a different way. You can straighten this up and have it as a domain wall in the bulb, such that if you fuse it to this boundary, it will change the boundary conditions altogether. And it will act on the lines puncturing it and change whatever is allowed to end before and after. But yeah, maybe the prescription for that operator is slightly convoluted, and maybe for those who are interested, they can wait when it appears in our paper, maybe a long time from now. Yeah, so I'll end there.
Okay, thank you.
The next period.